Hello, everybody. Welcome to our final topic on set theory. This is our set theory finale. We need to prove that two sets are equal. So given sets A and B, prove that A is equal to B. Now, this might not seem like a daunting task, but in CS 241, which is Discrete Mathematics 1, this is a very frequent question on tests, and students frequently get it wrong. So if we can teach you how to do it, well then, hopefully you'll be set for those exams. So, we have sets A and we have sets B, and we want to show that they're equal. So one way that someone might think to first try is to show that for every element, so for every, we'll say, little a inside of our set A, so this is every single item in A, we want to show, so if A is also in B, then that means that A equals B. So this is the first way that someone might think to show that two sets are equal. You take all the things inside of A, and you say, well, are all of the things inside of A inside of B? Well, if so, then they're equal. And this would make sense because that's like a logical way of going about it. When you work with numbers, say we want to say, is 2 equal to 2? Well, this is the same as that. So if this is the same as that, well, we know that that is the same as this. Makes sense to me. Unfortunately, this, and let me get it with some orange, is not the case for sets. Sets, and you know what? Let's go through an example to show why this is not sufficient. Let's say that A is equal to the set 1, 2, and B is equal to the set 1, 2, 3. Now I would pause the video here and maybe try to prove to yourself why this now is not enough, and you can use these two sets as an example. Moving on, it's pretty clear that the sets A and B are not the same set. This set has a 3 in it. But everything inside of A is inside of B. So 1 is inside of B, and it's inside of A, and 2 is inside of B. So we can say that for all A inside of A, well, A is in B, but our two sets are not equal. So we need something else. We need another condition added on in order to show that our two sets are in fact equal. So not only do we need to show that every A inside of A is inside of B, but we also need for every B inside of B, if, and you know what, let me erase this because that doesn't imply. And I'm going to add in this and. If B in A, then A equals B. So what this is saying is, for every single A in our set A, if A is also inside of B, and if for every B inside of B, if B is inside of A, well, then our two sets are equal. And what is this saying? So for our example before, everything inside of A is inside of B. But not everything inside of B is inside of A. So if we were to select this, this is not inside of A. So what if we were to remove 3? Well, everything inside of A is inside of B, and everything inside of B is inside of A, so our two sets are equal. And looking at this picture, it's pretty obvious that our two sets are equal. Now, we can also compact this notation a little bit. If everything inside of A is inside of B, well, that just means that A is a subset of B. So if A is a subset of B, and if everything in B is inside of A, well, that means B is a subset of A. And if B is a subset of A, well then A must be equal to B. And this might seem strange because subsets, you think of them as being smaller. But subsets can be equal. It's as if we said, we had our real number case, we said x is less than or equal to y, but y is also less than or equal to x. Well, since x is less than or equal to y, if we were to draw that on a number line, x has to be here, if this is y, so x has to be here, but if y is less than or equal to x, well then y has to be here, so the only place that they cross is there. And the same thing goes for this. Now, let's go into the basic structure of how to actually show that two things are a subset. Okay, so the general steps we're going to have to show that A is equal to B is we need to do two things. So we need to show that A is a subset of B. So we're going to pick arbitrary A. And when I say arbitrary A, I don't mean pick like a particular value. So from our past example of set 1, 2, you don't pick 1 as your A. You just pick anything. You say A is a variable. That can be anything inside of A. And we need to show that A is also inside of B. The second step is just doing the opposite. Pick an arbitrary B in B and show B is in A. And then that's your proof. It's not complicated. I think anyone can do it. So I believe in you, and we're going to go through an example problem. All right, so we're going to prove this claim that A intersect B union C is equal to A intersect B union A intersect C. So this is the distributive law, but we're going to prove it. We're going to prove it. So our first step is to show that this is a subset of this. So we'll say pick some x inside of A intersect B union C, right? So if x is inside of B union C, or intersect B union C, what can we gain from this? This implies that x is inside of A and x is inside of B union C, right? Because it's the intersection. So the intersection is the combination of all things that are inside of both sets. So if x is inside of this full thing, it has to be inside of both of them. And well, what does this mean? Well, that means that x is inside of B or x is inside of C. And well, if x is inside of A and x is inside of B or x is inside of C, well, that means that x must be inside of A intersect B or, which is the union, A intersect C. And if that step wasn't easy to follow, that's because what you do is you say x is inside of here, guaranteed. You know it for a fact. But x is inside of this one or it's inside of this one. So if x is inside of A and B, well then it's here. But if x is inside of A and C, it's in here. So we just union them together. So from that, we know that A intersect B or C, or union, this is union, C is a subset of A intersect B union with A intersect C. Now, we need to show the reverse. We need to show that this is a subset of this. Okay, so now we're going to show this. So if y is inside of this big thing, well, this is a union, so we know that y has to be inside of A intersect B, or y is inside of A intersect C. Well, if y is inside of A intersect B, or y is inside of A intersect C, also note it could be inside of both of them, well, we know since it's inside of the intersection and both of them contain A, that y must be inside of A. And if y is inside of A and it's inside of at least one of these quantities, well, y must also be inside of B or C. And to say that y is inside of B or C, we say it's inside of their union. Well, if y is inside of both of these, we know that it must be inside of its intersection. So y is inside the intersection of A and B union C. And from there, we just showed that now this is a subset of this. And since we know that this is a subset of this, and before we showed that this is a subset of this, we know that A intersect B union C is equal to A intersect B union A intersect C. This is the distributive law. And we could even put the fancy QED, or you can put the proof square. Some people do square. But I personally will do that little signature. That's not even my initials, but I messed up my initials once, and I just had to stick with it for the rest of my life. And with that, that is the end of set theory. This is pretty much all you need for your general classes. I mean, set theory is a broad topic, so it goes much deeper than this. But for now, this is all we will be covering. So from here on, we're going to be moving into a little bit of abstract algebra, and we're going to be talking about things like operations, relations, functions, and maybe even a bit of groups. So I hope that you keep watching. Thank you.